Hello and welcome, class. We today are going to be jumping into a new chapter, Chapter 7, where in our previous couple of chapters we've been working with crystalline structures, with molecules, with learning how to draw them, and in Chapter 7 we're really going to round out that picture before moving on to chemical reactions by acknowledging the fact that these molecules that we have been working with in drawing exist on paper so far in a two-dimensional space. In reality, these molecules exist in 3D, so we're going to have to talk about what the shapes of these molecules are, what the implications of the shapes are, and as a result, what the molecular reactivity is dependent on the shape. Alright, so before moving into reactivity though, let's really focus on what these molecules look like in 3D space. Alright, so again, our Lewis structures, what we have been drawing, exist as two-dimensional models. We draw them, right, on paper, we can illustrate them on the computer, as I have here, but the picture of this, let's say for example, CH4 molecule, in 2D, is not quite an accurate picture of what the molecule looks like. For example, if we were to measure the bond angle, of which the definition is here, this is the angle defined by the chemical bonds relative through the central atom. We measure the bond angle from hydrogen to carbon to hydrogen. What we find is a 90-degree bond angle in 2D. Now this is well and good, but the problem is that in 3D, the molecule actually buckles out in the third dimension. We do not have perfect 90-degree right angles from hydrogen to carbon to hydrogen. In fact, the bonding angle in the actual geometry of this molecule, from what we've been able to experimentally gather, is actually 109.5 degrees. So the bonding angle is larger than what we would predict just using our 2D model. Our real structures exist in 3D. So what we're going to be talking about today is, depending on the arrangement of the atoms in the molecules, how can we predict, without needing to explicitly look at the molecule each time, what the actual 3D geometry is going to look like? Now this prediction, or our ability to predict the 3D geometry of our molecules, is explained by VSEPR model, where VSEPR is actually an acronym that stands for Valence Shell Electron Pair Repulsion Model. So what we are doing here is observing the valence shell of each of the atoms in our molecules, observing where the electron pairs are around the central atom, specifically in the molecule, and predicting how these electron pairs are going to repel each other. Right, electrons are negatively charged, and they are physical particles. They cannot exist in the same place at the same time. As such, the premise of VSEPR model, or VSEPR theory, is that the electron groups are going to spread out in order to minimize the repulsion that is experienced within a molecule. So how these things are going to spread out is not just, again, in 2D, but rather they are going to spread out in 3 dimensions. They're going to spread out in 3D. How we can predict where the electron, or rather how we can, observe where the electrons are and therefore predict how they are going to spread out, is by observing what the steric number is around the central atom. So the central atom is going to be the one that has, as we discussed in Chapter 6, has the largest bonding capacity, is placed in the center of the molecule. It's where all of the bonds or lone pairs are kind of radiating out from. So if we observe the steric number of some central atom, for example, oxygen inside of this water, since it's where the bonding pairs are coming out from, we can see a couple of lone pairs here. The steric number is going to be equal to the number of bonding groups we have, in addition to the number of lone pairs we have. So a bonding group is a location where bonds can be. This is the same kind of definition of a bonding group that we observed in Chapter 6 when discussing the bond order and resonance structures. So what we're looking at is, where can the electrons be? we can see that there is a clustering of an electron pair between the oxygen and hydrogen on the left. There is another clustering of electrons between the oxygen and hydrogen on the right. So our number of bonding groups in water around the oxygen is equal to 2, and the number of lone pairs we can see is also equal to 2. We have 1 lone pair, 2 lone pairs. So notice we're not counting individual electrons, we are counting pairs of electrons. Or when it comes to the bonding pairs, we're looking at where the electrons can be. We're just looking at pockets of electron density. So the number of bonding groups equal to 2 plus the number of lone pairs equal to 2 gives water a steric number equal to 4. Now this 4 is going to tell us what the geometry of the electron pairs are around the central oxygen inside of this water. So let's start observing all of the different kind of combinations for steric numbers that we can have, bonding groups and lone pairs, and kind of partnering these numbers, these steric numbers, along with specific geometries. Before we get too ahead of ourselves though, there are 2 different definitions for geometry when it comes to molecules. The first is known as the electron pair geometry, and the second is the explicit molecular geometry. Both of these geometries are important when it comes to observing molecules and being able to predict their reactivity, certain chemical properties, their behaviors. So it's going to be important for us also to acknowledge both of these definitions before we actually start defining geometry pertaining to the molecule, right? We need to figure out what type of geometry we're even talking about. So the electron pair geometry is defined by the relative positions of the electron density around the central atom. This electron pair geometry is explicitly dependent on the steric number. There is a 1-to-1 correlation between an electron pair geometry and a steric number. So a steric number, let's say for water equal to 4, has one specific electron pair geometry, and we're going to define what that is in a second. Similarly, if we were to look at a molecule that had a steric number of 3, there would be one given electron pair geometry. It's always going to exist in this 1-to-1 correlation. Electron density around the central atom counts for both bonding pair locations and for lone pairs. So we're looking at where all of the electrons can be around this central atom. This is explicitly what gives us our steric number, as we kind of saw in the previous slide as we defined it, and as such, this steric number will give us one specific electron pair geometry. We don't need to pay attention to the difference between where the electrons are, whether they be in bonds or in lone pairs. Doesn't matter. If there are electrons, it contributes to the total count of the steric number. All right, the molecular geometry is defined a little bit differently. The molecular geometry is defined specifically by the positions of the atoms in the molecule around the central atom. So lone pairs will help to guide and repel these particular atoms into certain positions. However, the molecular geometry is only going to be paying attention to the locations of the atoms relative to the central atom. Again, these lone pairs up on top are helping to push the hydrogens down because the lone pairs need space. However, electrons are very small. Even if we could see atoms, the electrons themselves would be so tiny we wouldn't be able to see them. So really what we're looking at is the geometry of the bonding pairs, the geometry of where the bonds can be and exist inside of a molecule. So in the molecule, or the outline of this water up on top, we can see there are kind of 4 circled lobes, again giving us a steric number of 4 and one particular defined electron pair geometry. In the molecular geometry, we're just looking at this, at the bonding connections between the atoms, which gives us more of like a kinked kind of like mountain, upside down V kind of a shape for our water. So both of these geometries are a way to define what the shape of water is. Which one we're going to use is going to depend on whether or not we want to pay attention to the lone pairs and their existence around the oxygen, or if we're just looking at the molecule as a whole and kind of saying like lone pairs are there, but electrons are tiny, we're just looking at the shape that the atoms make relative to each other. All right, so let's start by discussing the electron pair geometries, since they exist in a one-to-one correlation with all of our steric numbers. Once we have those down and the basic shapes down, then we will start expanding into more of the exceptional molecular geometries. Okay, so our electron pair geometries can be seen down below. In this class, we are going to be paying attention to the geometries caused by these 5 different steric number options around our central atom. So is there a total of 2 electron pairs or 2 locations of electron density around your central atom? That is going to give you the shape down here. Do you have 3 locations of like electron density around the central atom? It's going to give you the shape here. 4, 5, and 6. So each of these steric numbers I have illustrated down below in the way, or in an approximate shape that reflects what the electron pair geometry of the molecule actually is. All right, so let's break down each of these shapes though. I'm going to clear the slide real quick. I'm going to break down each of these shapes, connecting it to the illustration down below, along with discussing where all of the bond angles can be found inside of these structures. So the first of all of our electron pair geometries is known as the linear geometry. This structure is known as linear because there are 2 electron groups around the central atom, and according to VSEPR theory, these 2 electron groups are going to spread out around the central atom as far away as they can from each other. In our illustration down below, we can see explicitly this occurring. There is no further distance or no further angle away that one of these electron groups can get from the other than 180 degrees. Right? If we have the 2 on opposite directions of the central atom, there's like we can't we can't change the angle. We can't have these 2 electron pairs, let's say, at a different angle and still be further away. So if we decrease the bonding angle, we can see that this electron pair group is going to be getting closer to the first. Similarly, if we increase the bonding angle, it is again going to be moving closer. Right, there's no further you can get away than 180 degrees across from some type of central point. So 180 degrees is going to be what the defined bonding angle is for some type of linear geometry. Now this molecule is going to end up looking like a straight line in 3D space. So we have a central atom, 1 atom or electron pair group on the left, another on the right, and this is our first electron pair geometry that we are going to define. The next up is if we are looking at a molecule where the steric number around the central atom is now 3, this is going to correspond to what we call a trigonal planar geometry. Each of the bonding angles inside of this structure is going to have a bonding angle of 120 degrees. In the structure that we can see illustrated down below, we have our central atom again in gray, and each of the surrounding atoms or electron-dense groups presented in blue, and the bonding angle from one through the central to the next is 120 degrees. This is equal to the angle inside of a triangle, hence why we call this a trigonal planar. If we were to connect the dots between each of the atoms here, we would see that we have actually created a triangle. Each of the atoms inside of the structure do exist in the same plane. If we were to lay down this molecule, it would appear flat and it would just sit flat on top of some type of surface. The bonding angle of 120 degrees, in much the same way as the linear case, is as far away as each of these atoms can get from one another without starting to get closer to something else. So 120 degrees geometrically is the most stable bonding angle for any type of molecule that has one central atom and 3 different electron domains or electron pairs or electron groups around it. All right, next up, we have a structure known as a tetrahedral structure, which corresponds to a steric number of 4. In a tetrahedral structure, the illustration down below doesn't look the best in 2D, so what I'm going to do is go back a little bit to here, clean this up. The structure that we have illustrated here for CH4 is also what we call a tetrahedral geometry. We can see in this geometry we have one bonding pair, or one atom in this case, pointing straight up, and then the other 3 are kind of forming a base of a triangle, but still below this central atom. If we connect all of these dots together, what we actually end up with is a tetrahedron geometry. There's the last one. This tetrahedron geometry in math is where we get the name tetrahedral. Each of the atoms here is pointed along the vertex of a perfect tetrahedron, where our central atom is or exists exactly inside, like in the central point of that tetrahedron. So the tetrahedral geometry that we can try and illustrate in 2D like so, where we have one atom pointing directly up. This one that's coming down is actually kind of coming out of the plane of the board, or out of the plane of the slide, and both of these two on the left and right are kind of going backwards. They're out of the slide in the back. So if we were to connect the vertices like so, we would similarly end up with a, as I have kind of informally drawn here, a tetrahedral shape, where the central atom here is again inside of the tetrahedron. Now, if you have trouble seeing, looking at things in 2D and visualizing them in 3D in your head, I would absolutely recommend that you kind of either pull up, on Wikipedia or Google in general, what the shape of a tetrahedron is, or even see if you can't find some type of 3D site where you can interact with tetrahedral molecules, trigonal planar molecules. This is going to supplement this lecture that I'm giving in a really powerful way if you, again, have trouble kind of visualizing things in 3D. All right, the bonding angle between each of the atoms, though, in this tetrahedral structure, so I'm gonna erase a little bit of it. Don't want to get rid of too much there. The bonding angle inside of a tetrahedral structure, from up to the center down to the right, is 109.5 degrees. And that is true for each of the bonds presented here. Again, in 2D, it does not look like each of these bonding angles is 109.5, at least not with the illustration as I have it drawn here. But if we go back, it becomes a little bit more obvious that each of these bonding angles is actually the same. They are all the same measurement, and they are all 109.5 degrees. The trigonal bipyramidal and the octahedral both are exclusively geometries for expanded octets. We can have, as we will see, some expanded octet geometries with lower steric numbers, but if we are working with larger steric numbers, you have to have an expanded octet to get here. So it would be impossible for an element, let's say, like carbon, which has an atomic number less than 13, which cannot expand its octet. The element of carbon can never have a steric number of 5 or 6. It cannot form these larger, more expanded geometries. All right, so the first of our large geometries is known as the trigonal bipyramidal. This is a longer name, a little bit more complicated, so let's kind of break it down a little bit. Well, trigonal means that we're going to have a triangle somewhere inside of the structure, much like how the trigonal planar structure had a triangle formation. So the trigonal bipyramidal structure, we can find where the triangle is by connecting these 3 dots in the center. What this structure looks like in 3D is we're going to have a kind of equator around this central atom that is comprised of 3 atoms that are exactly in the same plane as one another. It's actually going to have the same geometry as the trigonal planar structure, just laying down along the equator here. We are then going to have one atom pointing directly up and another atom pointing directly down. The bipyramidal aspect of the name refers to the fact that we have a trigonal base and one pyramid up above, and a second pyramid down below. So this is where the trigonal bipyramidal name comes from and how it can be used to kind of connect and visualize the structure. The bonding angles that we can see inside the structure, I'm going to clean a little bit of this up, but still keep the equator in place since I think it's actually kind of helpful to see where the trigonal aspect is inside of this molecule. The first bond angle of 90 degrees is from the either top atom to this equator, 90 degrees, or from the atom that's pointing directly down up to the equator. Right, since this equator is perfectly perpendicular to the atoms that are pointing up and down, these are going to be where the 90-degree bonding angles are. The 180 bonding angle then, or 180-degree bond angle, comes from adding up these two 90 degrees together, right? So the angle from the upper atom all the way down through the center to the bottom is 180 degrees. The last bonding angle of 120 degrees we can explain by observing the angles between the atoms that are actually in this like triangular plane, right? The 120-degree bond angle comes from the trigonal planar nature of the like equator atoms all relative to each other. So the 120-degree bond angle is going to be from this atom through the center out to any of these other planar atoms, like so. All right, last but not least, we have the octahedral geometry. This corresponds to a steric number of 6, meaning that we have 1, 2, 3, 4, 5, 6 atoms around our central atom, or 6 locations of electron density around our central atom. This structure is named octahedral, not because there are 8 atoms around the center, but instead because if we were to add or connect each of the lines here, as I am doing, connecting the dots, what we end up with is an octahedral shape in 3D, an octahedron. For anyone who is a little bit nerdier than most, this type of geometry is what the like D8 dice looks like. So if you have some type of D8 dice, or if you just like Google real quick what a D8 looks like, it is the perfect octahedral example. There are 8 faces on an octahedron, where each of the atoms present in this octahedron are like the vertices that are connecting the faces, the vertices that are putting this like octahedron together. So the octahedral geometry has 8 faces if we connect the dots, but only 1, 2, 3, 4, 5, 6 atoms around the central atom that are the vertices of this octahedron shape. All right, the bonding angles of 90 and 180 degrees arise from the fact that all of the individual bond angles from, like, let's say the top to the center, out to any one of these sides, all of these bonding angles are perfect right angles. This bonding angle is a perfect 90 degrees. And that is true for each of the top to center to midpoint bonding angles. If we go from top to center down to bottom, this bonding angle here from top down is a linear geometry. It is a perfect 180 degrees. All right, and if we wanted to draw the bonding angle from, like, let's say this point in the back through the center to the point in the front right, we would be able to tell that this is also a straight line, which is also going to be 180 degrees. So we have like 90-degree options and 180-degree options in the octahedral geometry everywhere. So the octahedral geometry is going to be the largest electron pair geometry that we are going to observe. And again, if you have issues with looking at things in 2D and trying to visualize them in 3D, Google is your friend. There are so many options online, either through Wikipedia or more like, let's say, niche academic websites where people have put together like interactive like models where you can spin these things around, you can really see how they look in 3D, and I would absolutely recommend checking out any of those options on Google, doing kind of like a cursory search on your own. All right, so these are the electron pair geometries. In each of these cases, these like blue atoms or these blue spheres outside of the central atom, could represent an atom, or they could represent a lone pair. All that matters is that this is the location of some type of electron density above or around the central atom in some way. All right, so let's look at some examples then of molecules, observe what their steric numbers are, and then determine what the electron pair geometries for these three examples are before we move forward with the, let's say, slightly more specific molecular geometries. All right, so do your best. Look at the central atom, so boron, sulfur, and phosphorus. Determine how many electron groups there are around the central atom, and then figure out what its electron pair geometry is from that steric number. All right, welcome back from the fold. Let's start with our molecule here on the left. This is the molecule of BF3, Lewis structure, happily given. So what we're going to do is observe how many electron groups there are around each of the central atoms, the boron, the sulfur, and the phosphorus, starting with the boron. Well, in boron's case, or in this boron trifluoride case, we can see that there are 3 different bonds to the fluorines, and there are no lone pairs on the boron itself. Because there are no lone pairs on the boron, there are only 3 bonds around it. The steric number of this central boron is equal to 3. Since we have a steric number equal to 3, in order for these bonds to spread out as much as they can in 3D space, just to go back and look at our table that I'm going to clean up right now, the steric number of 3 corresponds to a trigonal planar geometry, which means that the molecule is going to have this shape in 3D. There are going to be 120-degree bond angle or bond angles between each of the fluorines as they surround this boron and spread out as much as they can. So our BF3 is going to have an electron pair geometry that is trigonal planar. All right, let's turn our attention to SO2. We can see that this central sulfur, yes, has expanded its octet. However, we are going to be looking for where the electron groups are. Where are the electron groups surrounding this central sulfur? Well, we can see that there is a lone pair up on top. There is a double bond down to the left and a double bond down to the right. Notice that I am not counting the double bond separately. This is one location. We are looking for the locations of where bonds are, not counting the numbers of electrons themselves. So we have one location down to the left, and we have another location down to the right, where another double bond is present. We have circled 1, 2, 3 locations for where electron densities can be, where we can observe that they are. This means that our steric number for our SO2 is also equal to 3. And a steric number equal to 3, if we go back upwards, corresponds to the exact same geometry that we just observed for the BF3. We are looking at a trigonal planar electron pair geometry. So our steric number equal to 3 means that we have a trigonal planar geometry. Right, and I did say that the steric numbers of 2, 3, and 4 correspond to molecules that are, at the very least, not expanding their octet, but it doesn't mean that expanded octets can't have these lower geometries as well. The higher level geometries must have an expanded octet. That is the rule. That is a prerequisite to have a steric number of 5 or 6, is you must have an expanded octet. If you have electrons kind of doubling up, like we have in this sulfur dioxide case, we can actually end up with a lower steric number, despite the fact that the central element has an expanded octet. So this is a really good example of kind of like, in form of an analogy, it's like how a square is always a rectangle, but rectangles aren't always squares. Here we have a steric number of 3 corresponding to an expanded central octet. All right, the last geometry we have to observe in terms of electron pair geometry is this phosphorus pentachloride, this PCl5. Now, just like before, we're going to observe where electrons are surrounding our central phosphorus. We can see that the chlorines are, some of them are like coming out of the plane of the slide. That's what this like big wedge means. Some, or one of these chlorines is going back behind the slide. So this is behind, and this is in front. It is our way of trying to illustrate the shape of these bonds, like how they're actually oriented, even though it's in 2D space, because it's a 2D drawing. All right, so let's count how many bonding pairs we have, or how many locations of bonds we have, how many locations of electrons around this phosphorus. You can see we have 1, 2, 3, 4, 5. There are 5 bonds and no lone pairs, meaning that our phosphorus pentachloride has a steric number equal to 5. So this is a great example of how we have a central element that has an expanded octet, and all of these electrons are actually spread out in 5 different unique locations. Because the electrons are spread out in 5 different unique locations, we are going to be working with, to go back to our table, steric number of 5, a trigonal bipyramidal geometry, this one right here. Right, a trigonal bipyramidal structure. So our chlorines up above and down below are right 180 degrees from each other. The chlorines that are presented here are kind of in this trigonal equator, even though they're not drawn exactly like that in 2D, right? Again, that's the limitation of trying to project a 3D image into 2 dimensions. There's always going to be a little bit of warping. All right, so if anyone has any questions thus far, if you were in my class, please do not hesitate to either leave a comment down below or shoot me an email directly. If you are not in my class, absolutely, please leave a comment below. I can do my best to try and explain or provide exterior links for like where we can rotate, and see these molecules in like 3D space. All right, so now we have talked enough about these geometries in terms of the electron pairs to kind of break it down even further and discuss molecular geometries. First and foremost, the molecular geometries for a particular molecule are going to be the same as the electron pair geometry, so it's going to be directly dependent on the steric number, in other words, when there are no lone pairs present on the central atom. So for example, methane, or CH4, which we have illustrated here on the right, there are 1, 2, 3, 4 kind of bonding groups around this central carbon. Because there are 4 bonding groups around the central carbon, our steric number is equal to 4. And as we've previously now discussed, that means that it would have an electron pair geometry that is a tetrahedral geometry. Now, according to our definition that we've just discussed here, it also means that the molecular geometry is also going to be tetrahedral. And this is because, according to our previous definition that we've already outlined or discussed, right, defined, the molecular geometry is defined by looking at where the positions of the atoms are around the central atom. So in this case, the number of electron pairs is equal to where all of the atoms are. And this is going to give the molecule the exact same geometry definition in both cases. Where the molecular geometries will differ when they become a little bit more specific is when lone pairs are present on the central atom. So again, something like water, where we can see it also has a steric number of 4 since we have 2 lone pairs and 2 bonding locations. It's going to have a different molecular geometry because we're only going to be paying attention to the atoms in this case. Again, this is not to say that the lone pairs don't impact the locations of these bonds. The lone pairs are going to want to push away and repel the hydrogens and their bonds, right, as much as possible, so everything can spread out in 3D space. But if we're actually just paying attention to the locations of the atoms, it's going to look differently because we're ignoring the impact of the lone pairs on the shape. All right, so let's break down some of the more specific molecular geometries when lone pairs are present. Again, our first rule up here, the molecular geometry is going to be the same if there are no lone pairs, so I don't think that needs any further discussion. The more specific examples occur when lone pairs are present. So this is our question now. Does your structure have a lone pair? If it does, this means that the molecular geometry will be different than the electron pair geometry. All right, so we're going to break this down by electron pair geometry. We're going to break this down by steric number. So the molecular geometry is almost like a subset to the electron pair geometry. So if our first electron pair geometry, corresponding to a steric number of 3, is trigonal planar, there's only one way that we can substitute, let's say, a bond for a lone pair to get a unique geometry that still contains 1, 2, 3 different atoms. This geometry, this molecular geometry, we call bent. So the SO2 example we actually just looked at, right, a couple of slides ago, had an electron pair geometry that was trigonal planar. Right, there are 1, 2, 3 electron locations around the central atom. However, if we're only looking at the atoms as they are arranged inside of the molecule, we can see that there is a breakdown of 2 bonding groups right here, and there is 1 lone pair, and this lone pair is going to be pushing down on these 2 oxygens and their double bonds that they are experiencing. So the bond angle that we would expect to see from oxygen to sulfur to oxygen is going to be approximately 120 degrees. Since we are not working with a molecule that has, like 3 identical sulfur to oxygen bonds present, we're not actually going to see a perfect 120 degrees. We actually see something that is a little bit less than 120 degrees. But what's important to acknowledge is that we are still in that 120 degree ballpark because the base geometry is trigonal planar. It just so happens that this 1 lone pair is going to be pushing these 2 bonds out of a linear conformation and into something that we call a bent conformation. All right, so the sum of the bonding groups and the lone pairs, again, should be equal to your overall steric number. So if you're given like a chemical formula, like if you were to start from scratch and I say, hey, identify the electron pair and molecular geometry for SO2. You can draw SO2, observe how many bonding groups and lone pairs there are relative to each other, and use that to identify what the molecular geometry is. You can add the bonding groups and lone pairs together, figure out what the total steric number is, and that's going to tell you what the electron pair geometry overall will be for SO2. So each of these definitions is working, or I should say both, I guess, of these definitions are working together, and all we're doing is looking at bonding groups and lone pairs. All right, so this is the bent geometry that falls underneath the category of the trigonal planar electron pair geometry. Let's look at a different molecular geometry. All right, so underneath the electron pair geometry umbrella of the tetrahedral shape with a steric number of 4, we actually have 2 different unique molecular geometries that we can find. And again, all we're doing here is substituting out chemical bonds for lone pairs. So there are actually 2 different configurations that we can get, either 3 bonding groups and 1 lone pair to get a total of 4, or 2 bonding groups and 2 lone pairs to get a total steric number of 4. The first case, the trigonal pyramidal case, corresponds to the NH3 that we have below, and the bent, where we can see we have 2 bonding groups and 2 lone pairs, is going to correspond to the water that we have over on the right. Now I'm going to erase the arrows that I just drew. All right, so let's illustrate where these shape names are coming from. First and foremost, the trigonal pyramidal shape. Again, we have the word trigonal present. This is because there are 3 bonds that can be connected via a triangle. So hydrogen to hydrogen to hydrogen makes a perfect triangle in the base. The reason why this is called trigonal pyramidal is because the nitrogen is actually up out of the plane of the triangle that is formed by the hydrogens, and it is going to form like the peak of the pyramid that we can draw. So it is a pyramid that has a trigonal base, hence why it is called trigonal pyramidal. The three bonding groups are held down underneath the plane of the nitrogen by the lone pair up on top. So again, this is where the electron pair geometry of tetrahedral comes from. We can imagine this lone pair existing up on the top of this nitrogen, and it's going to be pushing each of these hydrogen bonds down underneath the plane of where the nitrogen is. This is what's going to give us that nice pyramid with the trigonal base. The bonding angle from hydrogen to nitrogen to hydrogen is going to be a little bit less than 109.5 degrees. All right, for the same reason as the SO2 previous bent example, we would expect to see a bonding angle that is pretty close to that of the normal electron pair geometry, right? Since a tetrahedral shape has a bond angle of exactly 109.5. But since we don't have another NH bond up on top, the distribution or the repulsion experienced between like the lone pair and the bonds is actually slightly asymmetric, and so we're going to end up with a bonding angle just underneath 109.5. All right, in our water case, we can see that we have two bonds and two lone pairs in much the same description as our NH3 here. The lone pairs are going to push down on these hydrogen or the bonds between the oxygen and the hydrogen. This is going to contract our bonding angle from hydrogen to hydrogen, also to be a little bit less than 109.5 degrees. Since the steric number is equal to 4, we would expect the base angle to be 109.5, but again, because we have this asymmetric repulsion between our electrons, between the lone pairs and the bonding pairs, we actually see a little bit of a contraction again, a bonding angle that's a little bit less than 109.5. What these specific differences are, how far the bonding angle distorts away from 109.5, will exactly depend on how many lone pairs there are and what the bonds are constructed from. Do we have an N connected to 3 H's? Do we have a P connected to 3 H's? Since the distortion really depends and is molecule specific, like it depends on the atoms that are there, we're not going to be discussing what the specific bond angles are, because I don't want to give the impression that anyone has to memorize any of these like specific bond angles. Just so long as you know that we're working, or that when we are working with trigonal pyramidal or bent structures, the bonding angle is going to be a little bit less than 109.5. That's what I'm expecting you guys to remember. As we increase in steric number again, we can see that we now have introduced a third configuration, a third unique molecular geometry underneath the umbrella of the electron pair geometry of the trigonal bipyramidal shape. So again, our steric number here is equal to 5, and in the event that each of these 5 electron groups is formed by a bond, then the electron pair geometry would match the molecular geometry, both would be trigonal bipyramidal. In the event that a lone pair becomes present, we could have 1 lone pair, we could have 2 lone pairs, we could have 3 lone pairs, but these are going to be the only unique combinations that we can form before we start losing too many atoms and we don't actually have anything that makes like a good shape. So in the event that we have 4 bonding groups and 1 lone pair, we call this shape the seesaw shape. In the event we're looking at a molecule that has 3 bonding pairs and 2 lone pairs, we call this the T-shape. And when we have 2 bonding groups and 3 lone pairs, this is actually another way to make a linear configuration. So we have 3 different illustrations down below, and we can kind of pick out where each of these like shapes is kind of coming from. So in the seesaw geometry, where we have 4 bonding groups, we can see that the 4 bonds that remain around this central tellurium, for example, is a chlorine that's pointing up, a chlorine that's pointing down, a chlorine that's kind of coming out of the plane towards us, and a chlorine that's going back into the plane behind us. The lone pair that's present is also in this equator. So a lone pair has substituted out, right, it's tagged in replacement for one of the chlorines that normally exists inside of this trigonal like equator around the central point. The reason why the electron pair is here is because it allows for more space. Lone pairs love to have space, right? They're not confined in a chemical bond. They're not forced to exist, or I should say they're not, they do not exist. It's not like they're forced, right? It's the most stable configuration. That's why bonds are formed in the first place. Our lone pairs, though, do not exist between two different atomic centers. They're just located at one atomic center. This means that they're allowed a little bit more free range to roam. So since they take up a little bit more space, naturally when a lone pair occurs around a central atom, it's going to opt into the location that's going to allow it to actually spread out as much as it can. The remaining atoms then are going to be in the remaining locations. So we have 4 bonds, one pointing up, one pointing down, one coming out of us to the left, one going back behind us, one coming up towards us on the right, one back behind on the right. If we were to tip this shape over, what it would form is a little seesaw, right? If we had a chlorine down here, chlorine, chlorine, and a little tellurium right at the fulcrum, this is where the seesaw name comes from in the seesaw shape, and it's the lone pair that's sitting right up here on top. All right, the T shape is the shape that arises when we have 3 bonding groups and 2 lone pairs on the central atom. So we can see there are 1, 2, 3 bonding groups forming a T, and the 2 lone pairs are present up here on top. So both of these lone pairs are in the trigonal equator again, because it allows them more space. They have an extra degree of space because the atoms in the central equator are all separated by 120-degree bonding angles, whereas if the lone pair were to exist, let's say here, it would only have a 90-degree separation. So the bonding pairs around the equator are what gets swapped out for these lone pairs. They allow for more space. The resulting shape, though, of the atoms in the molecule are T-shaped. We have this really nice 180-degree separation here and a 90-degree separation here. This gives us a really nice T. All right, last but not least, under the trigonal bipyramidal umbrella, we have a linear structure. This occurs when we have 2 bonds and 3 lone pairs, and we can see that the lone pairs have now completely substituted out for the bonding pairs in this trigonal equator. This again allows the lone pairs to have as much space as they need, since they're all going to be 120 degrees apart from each other. They're still going to be 90 degrees apart from the bonds on top and down below, but it's kind of a little bit of a consolation since they do have that 120-degree spread inside of the equator. The 2 resulting atoms, or bonds, around the central atom then form a linear shape with a 180-degree separation between the iodine on the left and the iodine on the right. All right, so these are the 3 subsets that can be formed and do kind of readily form in some of these more expanded octet examples where we have a ton of electrons present around the central atom. Our last electron pair geometry umbrella to discuss is that of the octahedral geometry, where we have a steric number of 6. The breakdown that we have here, the configurations that we can make between our number of bonding groups and numbers of lone pairs, experimentally we actually find that there are commonly only 2 subsets or 2 molecular geometries underneath the octahedral umbrella. The first is known as square pyramidal, and the second is square planar. The first arises if we have 5 bonding groups and 1 lone pair, right? We add those 2 things together. This is where the steric number of 6 comes from. And our second is if we have a total of 4 bonding groups and 2 lone pairs, we add those together, and again, that's where their steric number of 6 comes from. Down below we have 2 examples, one for each of these geometries. The first is our square pyramid. The reason why this is called a square pyramidal structure is because our 4 fluorines form a really nice square. The xenon is in the same plane, so we have a really nice base or a square base for a pyramid, and it's the oxygen that exists kind of coming up out of this plane. the lone pair that exists hovers directly underneath the square plane. So our lone pair is suspended underneath the 4 fluorines in the xenon, keeping all of the fluorines in place. Our bonding angles we can see here are not expected to change, since this lone pair underneath the pyramid actually has plenty of space to spread out, so much so that it doesn't really have an effect on these 4 fluorines here. Last but not least, our xenon tetrafluoride we can see, and yes, this is a noble gas that is forming some type of chemical bond. We're kind of breaking the octet rule here to do so obviously we're going to have an expanded octet geometry to do this. Our xenon is going to be bonded to 4 fluorines, as we can see here, and each of these 4 fluorines presents a square shape. This is called a square planar geometry because everything is in the plane. Everything would lay flat on top of the surface of paper, let's say. We would just have a lone pair up on top and a lone pair group down below. Because we have an equal push from the lone pair on top to the lone pair down below, we actually see that this square shape, again, remains in the same plane. Everything is perfectly 90 degrees or 180 degrees apart. Oh, that was an intense ride. Again, if you need the time to kind of process each of these geometries in 3D, use any resource at your disposal. If you, again, are in my class and you would like, some suggestions for further sources, please do not hesitate to reach out and let me know if you have any questions or would like some supplemental materials. A couple of example problems I have listed here correspond to observing molecules and determining what their geometries are, so I would definitely suggest giving these a view. And if you ever need to return to to a table that has each of the electron pair and molecular geometries in it, again, if you're in my class using the 4th edition of Burge and Overby's Chemistry Atoms First, table 7.2 is where you want to go. All right, if you have any homework, please double check and do your homework. But until next time, class is dismissed.